Hello my friends and welcome back to Unip Education, the channel that makes psychological statistics accessible and, well, hopefully even fun. I'm Raffaele, your virtual psychologist and statistical expert, and here I am in another video. In today's episode, we will be diving into the exciting world of multiple regression. Yes, it's time to move beyond our previous tutorials on simple linear regression and take our analysis to a next level. So, what is the difference between simple and multiple regression? Well, in simple regression, we explore the relationship between one predictor variable and one outcome variable. You can call them as well one dependent variable and one independent variable. However, as aforementioned in the previous videos, when we're talking correlational measures, usually we are defining them predictor and outcome variable. Anyway, in other words, we're trying to predict the outcome based on one single input, this in simple linear regression. But in the real world, when is it that outcomes are influenced only by one factor? They are not. In reality, majority of outcomes are influenced by a plurality of factors. So, ladies and gentlemen, this is where multiple regression does its thing. Multiple regression lets us include several predictors in our analysis at the same time. So this helps us predict an outcome based on multiple inputs. So let me give you an example, very clear, very used one, just to clarify this. Let's say that we are interested in predicting college students' academic success measured by their GPA. In a single regression analysis, we might use just study hours per week as our predictor variable. However, we know that several other factors like class attendance, sleep hours, mental health, amount of hours spent on playing video games, etc., these things also play a role. So, using multiple regression, we can include all of these predictors in our analysis to get a more comprehensive picture of what predicts for real academic success. Today, we have a very interesting dataset for our analysis. A marriage counselor here is researching marriage satisfaction and wants to see how life satisfaction, happiness, and adaptability might predict it. Our outcome variable, or the variable we're trying to predict here, is marriage satisfaction, and our predictor variables, the ones we think might influence marriage satisfaction, are life satisfaction, happiness, and adaptability. So, what could the counselor's hypothesis be? Well, one hypothesis can be that all of them together significantly predict marriage satisfaction. What does this mean? It means that all of them at the same time are significant predictors of our outcome. However, while we are at it, multiple regression can handle more than just seeing whether all of them at the same time are significant predictors. Multiple regression can also check how much of the variance in marriage satisfaction each of these factors explain individually. So, the second hypothesis of our marriage counselor may be that life satisfaction will be the strongest predictor of marriage satisfaction. But let's go through steps. So now we go to Jamoli, and in order to conduct multiple regression, we will click as usual on regression. We will go into linear regression, and in this time, aside from picking marital satisfaction as our predictor variable or dependent variable, we will pick all of them at the same time into covariates. As you can see, Jamov is always helping you in specifying that in the covariate tab will go only the continuous variable or the ones with this ruler icon. If you will have like some nominal categorical variables, they would go into factors, but that's for another video. So, we still have, yes, the model fit and the model coefficients. However, just as you cannot build a strong house on a weak foundation, we cannot conduct a robust multiple regression analysis unless certain assumptions are met. What are the assumptions here? So let's check. We have autocorrelation, we will need this, collinearity, normality, residual plots, and Cook's distance. As you can see, these are all our assumptions. They are quite a lot in comparison to the previous test, but let's go one by one. So first of all, here we have Cook's distance. Cook's distance is basically displaying whether in our dataset there are a certain amount, or if any, outliers. In order to meet these assumptions, we should check the maximum number on the range, and this should be less than 1. In our case, it's good. It's 0.0573, and hence our assumption of outliers is not violated. Outliers can have a big impact on regression models by influencing our results. This is why we have these assumptions over here. After checking for outliers, we have to check whether the residuals in our model are normally distributed. And as you might know already, whenever it comes to normal distribution, our two friends always come to the rescue. It is exactly the Shapiro-Wilk test, which functions exactly as every other Shapiro-Wilk test. So in order for us to meet the assumptions, we should check whether the p is above 0.05. In this case, it is above 0.05, and hence we have respected these assumptions. After normality, we have one of the most important assumptions for multiple regression, which is the Darwin-Watson test for autocorrelation. What does this test do? It's testing the independence of errors. What does it mean? It means that the residuals or errors from our model should be independent of each other. So, in other words, the error associated with one observation shouldn't predict the error associated with another. Violation of this assumption usually stunts you from proceeding with further analysis, in as much as you will inflate type 1 error to the sky. So how do we interpret the Darwin-Watson test? Very simple. P should be above 0.05 as for the Shapiro-Wilk test of normality, so in this case it is fine. And the DW statistics should be around 2, meaning that values between 1.5 and 2.5 are okay. If they are like above or below, not the best. In our case, we have 2.08, and hence that is completely fine. Then we have the assumption of multicollinearity, which refers to high intercorrelations among independent variables. So when variables are highly correlated, it becomes difficult to tease apart their individual influences on the dependent variable. So, for instance, if you have hours spent studying and hours spent on video games, predicting GPA, they will probably be very related, as much as if you are studying, well, you're not playing. If you're playing, you're not studying. So, what do we do in this case? We probably pick only one of them as our predictor variables, or as our independent variables. So, how do we check it? We check the VIF, which stands for variance inflation factor, and this VIF value should be less than 10. So in this case, we have all scores way below 10, and that is completely fine. Otherwise, you can also check tolerance. And tolerance value should be above 0.1. In our case, they're all well above 0.1, like 0.1, so it is fine. Finally, we are checking the assumption of linearity and homoscedasticity of residuals. So in order to do this, we must check the fitted residual plot. Geomovie, unfortunately, as other statistical software, does not allow us to draw a fit or regression line, but you can see by the way these points spread across this plot that they sort of approximate a line, meaning in our case we have linearity and homoscedasticity of the residuals. What is homoscedasticity? You might remember this from the Levine's test of homogeneity of variances in t-test. It means that the variability in the residuals, in our case in multiple regression is about the residuals, is constant across all levels of the independent variable. If the variance of the residuals changes across levels of your predictors, it's called heteroscedasticity. homo, same, hetero, different from Greek, which can lead to inefficient estimates and incorrect conclusions about the significance of predictors. So, in this dataset, all our assumptions were met, and so we can proceed with actual regression analysis. So, once we've checked our assumptions, we can finally go into the regression analysis. So, we close the assumption checks tab, we will go into model fit, and here it's usually up to the statistician. However, I would recommend you for multiple regression to go with adjusted R-square. You can remove these two, or you can keep them if you prefer. And you also have to have the f-test in order to check the significance. Finally, we can check on the standardized estimates in order to test the second hypothesis, which the standardized estimate tab will give us, as you can see, like an estimate of each single predictor. So, as you can see from this table over here, which has all the predictors regressed on our outcome at the same time, as you can see, we have a significant result, meaning that all our predictors, meaning life satisfaction, happiness, and adaptability, can significantly predict marital satisfaction. And what about the variability? Well, we checked that through the adjusted R-square. And as you can see from here, in this case this is a percentage score, we can say that all these predictors explain 47.2% of the variance on marital satisfaction. So if our counselor's hypothesis was that all of them would significantly predict marital satisfaction, well, he was correct. And what about the second hypothesis? Our counselor here predicted that life satisfaction would be the strongest among the other predictors. How do we check that? Well, first of all, we must check the significance. In our case, we can see that life satisfaction, it is indeed significant, meaning it is an individual significant predictor. Happiness is also a significant predictor of marital satisfaction, whereas adaptability in isolation, it's not. So we can exclude adaptability and we should check which one is the strongest predictor, life satisfaction or happiness. We check the standard estimates over here, or also called beta values. I would always encourage you to call them beta values, but beta values end up to be, standard estimates. So in our case, since we have positive numbers, we can see obviously that life satisfaction is a stronger predictor, and as much as 0.57 versus 0.19 of happiness. In case, of course, we will have negative predictors, let's say, life dissatisfaction and sadness, so we will have negative scores. Obviously, the strongest negative would be working the same, so that would be like a minus. Well, it will work that way. But what about if we have life dissatisfaction and happiness? Well, in that case, if we have minus 0.5772 and 0.192, as you can see here, we're just adding a minus here, minus 0.5772 is still a stronger predictor, even if negative. So let's say here would be life satisfaction, and the hypothesis was life dissatisfaction would be a significant predictor, the strongest significant predictor. Even that one would be confirmed. And that's a wrap on multiple regression, folks. Remember, statistics isn't a sprint, it's a marathon. Each step gets us closer to our destination of making informed and evidence-based decisions for our research careers, or, well, let's be honest, just to pass our statistical courses. You all have a lot. Don't forget to click like if this video helped clarify these key concepts, and drop a comment if you have any question or topics you would like us to cover in the future. Hit the subscribe button and the bell icon to stay updated to our next videos. Until next time, I'm Raffaele, reminding you to always mind the stats, because numbers tell stories and it's our job to understand them. See you in the next one.